Hey, we're going to be looking at Chapter 20, Section B today. There's really not a lot here, and truthfully, I think this idea should have been introduced earlier in the text, but what do I know? I'm not an author. The idea here is that we can consider rates of change of lots of things. So we generally consider derivatives dy dx, that's the rate of change in y with respect to x, but we can use this idea of a derivative to figure out the rate of change of anything. And in the last video, we saw the rate of change of position with respect to time, ds dt, rate of change of velocity with respect to time, dv dt, and so on. So we could just have whatever, any sort of function of anything, we can calculate an instantaneous rate of change. Okay, let's just look at a few examples. Some of these are pretty straightforward and easy, but I do have one that I really like at the end. So, first one, okay. Some psychology, whatever. All right, so find the rate of improvement in ability to understand spatial concepts. Well, blah, 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 blah. Words, words, words. Find the rate means we're definitely going to be taking a derivative here and substituting in these values into it. And by the way, I don't even know what the unit for A is. It doesn't matter. Let's just figure these out. Okay, so we know what A is. We calculate dA dt. Easy to do. Now we substitute in 9 for part 1 or 16 for part 2 there. So the rate of improvement, whatever the unit is here, it's 1/18th unit per year for a 9-year-old, but it's 1/24th unit per year for a 16-year-old. What that means is that as we're at least comparing a 16-year-old to a 9-year-old, the 16-year-olds, their ability is improving less per year than the younger child is. You got that? We're going to talk about that a little more in parts B and C. So why does dA dt have to be 0 for in between 5 and 18? Well, I mean, dA dt clearly is only going to be it can only be 0, or no, it's never equal to 0. It can only be undefined when t is equal to 0. So put in any value for t, and we're going to have a positive number there. So it's true not only within this domain of 5 to 18, but that's the one that was specified up in the problem. And what does that mean? Well, it means that, according to the psychologist, our ability to understand spatial concepts is never getting worse. Our ability is always improving. It's always increasing. Great, isn't that wonderful? However, as we just established, the 16-year-old had actually a smaller rate of increase in ability than the 9-year-old did. And that has to do with our second derivative, because if we take the derivative of that guy right there, we're going to get something that is actually always negative for any value of t that we put into it. So we have a second derivative that's negative, and what that means is that our rate of change of ability, while it is increasing, it is also going to be increasing more slowly over time. Right? Maybe it'll help to like just kind of graph this thing really quickly. I'm not going to be too specific here, but look, it's a square root function, right? We got square root of t, so that means we have something looking approximately like this. Time, our ability. Yeah, so as we age, our ability is getting higher and higher, but the rate at which it's getting higher is going down. Okay. No big deal. Here's a popular application of calculus. If you take econ, then marginal cost is something that you're probably familiar with, or you will be later on in your economics course. We've got a cost in dollars, C of x, that tells us the cost depending upon some value for x. I don't even know what did they even tell us what x represents here? They don't. They do. It's producing X items. Okay, cool. And it really doesn't matter that they're breaking this cost down into labor and raw materials and fixed costs. That's irrelevant. I mean, the 2200 is obviously something that's fixed, but I mean these three terms are all dependent upon X. I don't care what they break down into. So find C prime of X. That's easy to do. We calculate the derivative. Great. There it is. Its units is dollars per item because this is the rate of change in cost, C of X, with regards to X, which was items. So what this means is that like as we make more and more items, the cost is going to be changing, but it's not changing the same amount for every item, because our rate of change here is not a constant. We can see this if we were to calculate C prime of various items. Here's C prime of 150. Okay, it's 14.38. I guess we grab a calculator, just put 150 into those. Wonderful. So again, this does not give us the cost of making 150 items, but it's telling us the rate of change in cost per item when we have 150 items. In other words, this is giving us not the exact cost increase for making that 151st item, but it is an estimate. If I lost you with that, let me just repeat myself. Because this is the rate of change in cost at 150, the rate of change in cost per item, that means if we were to add a single item, that is, make a 151st item, the increase in cost would be approximately 1438. Compare that to the actual increase in cost, because that's actually what we're going to calculate here in part C. C of 151, so the cost of 151 items minus the cost of 150 items, that gives us just the cost increase for that one extra item, and it's 1444. That's really close to our estimate. So this is one, I don't know, application of differential calculus that I never found to be that interesting because I've never studied economics. That's just me. Ah, thank goodness, some trigonometry. Give me something mathematical to look at. Now I'm excited. All right, I'm back in the game. So we've got a triangle here, and this angle theta is going to be changing, but the side lengths of 12 and 10 are going to remain fixed. So obviously the area of the triangle is going to change with regards to that angle. So let's find the rate of change in area with respect to theta. Okay, so first, what is the area of triangle? Well, it's using our trig definition here. We've got this as our function. We need to have a function first if we're going to do any sort of calculus, right? So area is now a function of theta. Awesome. We're going to take a derivative. So derivative of 60 sine of theta, it's going to be 60 cosine of theta. Okie dokie. Here we've got a little note from our friend popping up here. He points out that theta must be in radians so that the dimensions are correct. We're going to comment on that in a moment. He's right, though. So if we had here 60 degrees, we're going to change that to pi over 3 radians. All right, so then we drop that in here. Great. 60 times a half, it's 30 centimeters squared per radian of change when theta happens to be pi over 3 radians. If theta was equal to a different angle, when theta is equal to pi over 2, then the rate of change in area per radian is going to be different. So it is not a constant change in area as that angle gets bigger or smaller. Now, what's the deal with radians and degrees? Why couldn't we just put in Why couldn't we just think about this in terms of degrees? Well, um, you may recall that the trig formulas we have for calculus, they require us to be working in radians. They don't actually work in degrees. So I just wanted to discuss that very briefly. In order to do this, we're going to make up a function, which is going to be this underlined sign. Okay, underlined sign means the sign of x degrees. Sine of x just means the sine of x radians. So sine of x and undersine of x, they're different functions, but they're related to each other by this here. So the question is, what is the derivative of undersine of x? The derivative of undersine of x is equal to the derivative of sine of pi over 180 of x, which, using our normal differentiation rules, including the chain rule, gives us this here. But we can rewrite this second part as the under cosine of x. So the derivative of under sine is equal to pi over 180 times under cosine. So we have this extra constant coming out of it due to the chain rule. So I don't want to make a big deal about this because I don't think it turns up too often, but just in case, let's be careful. If we're doing calculus, the problem needs to be in radians, and of course our calculator needs to be set to radian mode as well. So if you ever had a paper 2 thing and you're doing calculus with trigonometry in it, it's got to be in radians. Do it in degrees, you're going to get totally wrong stuff. So that's it. I mean, really, section B has just got some other word problems about like calculating rates of change of something with regards to something else. So there's a lot of different contexts. They're all a little bit different. We should just read through them and practice a bunch so we get comfortable in a wide variety of situations. That's all.